now see what we've been doing. We are dealing with the second order circuits. What we've done first, find the mathematical model to this second order circuit. This mathematical model is a ordinary differential equation, and we give them a special name, state equation, in circuit theory. They don't use this term in differential equations course. So in this theory we are using some new terminology related to the physical world. So once we found the mathematical model, which is this ordinary differential equations, we are going to solve these equations. So we repeated here what you have done in differential equation course. That means to find a mathematical solution to an ordinary differential equation, you've got to find the homogeneous solution and then find the particular solution, add them up, find the general solution. So the new things that we introduce for this second order circuit in the mathematical solution is this. Just remind you what we have done and what we will be doing. One of them was this calculation of these k parameters. It should be done once you found the general solution. That is the same as you have done in differential equation course. In the calculation of particular solution, we said we use the circuit theory to easily find out the particular solution in a specific case. This specific case is this. If the independent source is DC source, then you can find out a particular solution easily. We explained that. I'm not going to repeat it here. We already done it. You could watch that video. I am trying to explain to you what we have done differently from the differential equation course. So another different thing that we have done in the calculation of these k parameters. In here, we are calculating state variables, derivatives in initial conditions. So state variables, derivatives is this, initial condition is this. We can calculate this initial condition by using the given initial condition. So altogether the number of initial conditions that we're going to have is going to be 4, and we've got 4 parameters here. We're going to calculate this parameter by using these initial conditions. In mathematical course, you have been using eigenvalues and eigenvectors for the calculation of the k parameters. And then we said that's the one method that we use it. In circuit theory, we are going to introduce a new method. Not new method, we say alternative method. Why it is alternative? We are saying the given circuit, which is this given circuit here, I can do the analysis of this circuit in a different way. What is this in this way? This is what we are going to explain right now. We are going to use the superposition theorem in the physical world and say that in our circuit we've got 2 independent sources, 2 energy sources. One of them independent source, the other one is the energy stored on the inductors currents and capacitor voltages. So if I find this energy stored elements energy solution, energy related solution in a circuit, and find the solution for the independent sources, add them up, I can find you when both these energy sources in. That's superposition. So this is what we are going to do. Next is going to be this. When the initial conditions are in, that means energy sources related to initial conditions. The solution we found is called the natural solution. So we're going to find that solution. The second one is energy sources related to initial conditions are going to be 0, and the independent sources in. Find the first solution. Summation of this natural solution and first solution gives us the natural general solution. So let's see in details this natural solution and other solutions. Go to open board now. Here you are. That is the circuit given to us. In this circuit, although it's not written here, so it is given here. That is make it a bit clear. So there is a initial condition for the capacitor. There is a initial condition for the inductor. So this is the mathematical model of the second order circuit. Now we are saying we will be examining this circuit in a different way, and an alternative way. This alternative way tells use the energy source related to initial conditions. So here you are, the initial condition. So the energy related with this initial condition is going to be 1/2 C times V0 square. For this one, 1/2 L times I0 square. So these are the energy sources now. So the other energy source was that independent current source, and we deactivated it. So the first one, we will be using these energy sources, not the energy comes from that independent current source. How I am going to deactivate this element? I am going to make it open circuit. When I make it open circuit, my circuit is going to be this. This circuit mathematical model is going to be this differential equation. What's the difference between those two? If you replace that IT equal to 0, so this is going to disappear, so you're going to end up with this. Now we are saying the solution for this initial conditions related solution is called natural solution. That is a physical case, isn't it? Why is that? Because I can set up a circuit like that. So this circuit solution is going to be solution, going to be a general solution for this circuit, of course. This general solution has a special name, natural solution. Now, if you remember, the homogeneous solution of this given circuit is going to be the same for this case, because in order to find the homogeneous solution for this differential equation, we were going to make this equal to 0. This also means that use this, isn't it? So, homogeneous solution calculation steps are going to be the same. So, what it is, you're going to find the characteristic root from this equation. For this special case, it's going to be this characteristic equation, and roots are going to be this. So if you write the roots here, so S1 and S2, so you're going to have these 4 parameters unknown. These are needs to be calculated, it says. Now at that step, we could say that there are 4 unknowns here, but I've got only 2 initial conditions. How I'm going to do that? The answer is easy. For the given circuit, that's the circuit, you can calculate the state variable's derivative initial condition from this differential equation. How are you going to do it? If you replace t with 0 on the left hand side, that's what is done here, and replace t with 0 on the right hand side. So you end up with this. Now what this 2 is capacitor initial condition and the inductor initial condition. So that is the one. And the other one, make it different color, maybe it is easier. That is this. So that means, since the A matrix, these are, when you give the numerical values, these are all known. So from these are also known, so this initial condition must be given to you. So that means you can calculate the initial condition of the derivatives of these variables. So what we have done, we have IL0 given, VC0 given initial conditions, and we calculated dVC dt0 and dIL dt0. So 4 unknowns, 4 knowns here, these are all known, we calculated those 2 right now, and we've got 4 unknowns, so we can calculate all this. We have done it for the mathematical solution, but different time. What I mean by saying with different time, in this here, in the mathematical solution, to find out these parameters of the homogeneous solution, you've got to calculate the particle solution, add those 2, find the general solution, and then calculate the k parameters by using the initial conditions and the derivatives initial conditions. In here, we are not trying to find any general solution. This is our solution, because there is no particular solution, there is no independent source here. So I will be directly using my calculations here in order to calculate this k here at that step, not keep it to the end. So if you do so, you're going to find the general natural solution. So what is next? Use the second source. Second source, the energy source. In this one, the energy source, let me, second energy source. Independent sources in general. In our case, this is independent current source. Current source. The solution that we are going to find for this, it's going to be force solution. So we are doing the superposition. We use the energy source related to initial conditions. In here, initial conditions are 0. Pay attention to that. Initial conditions are 0. That means you made equal to 0 this initial this energy source. So you are using this second energy source, this source. We are going to find this solution. That's for solution. Already we found the natural solution. Add them up is the solution of this given circuit, which includes the initial conditions and the independent source in it. So calculation of the first solution is the same as the mathematical solution. Why is that? The only difference is, in general, in the mathematical solution, we've got an initial condition. Now we made these initial conditions equal to 0 in this case. So all you've got to do, repeat what you have done in the mathematical solution. So this calculations here show that. That means repeated calculations. So this is the homogeneous solution. To find the homogeneous solution, you're going to make this one equal to 0. Find the characteristic equation. This is the characteristic equation. Find the characteristic root. So you're going to find the same characteristic root, the same characteristic equation, and the same characteristic root. So your homogeneous solution is going to be this, same as the natural solution. But we are not going to calculate this case here. What we are going to do, go a bit up here, find the particular solution. So I'll write it here, particular solution. That's the particular. So that is homogeneous. That's the particular solution. And then add them up. Here you are, homogeneous solution and the particular solution gives you the general solution. Now we are going to calculate these k values. How we are going to calculate it? We are going to use the initial conditions, this. So let me make it a different color. So these are the initial conditions. I will be using these initial conditions for the calculation of those two. So once again, there are two initial conditions here, inductor current, capacitor voltage. But we've got 4 Ks here to be calculated. So we need to calculate the initial conditions of the derivative variables. So I'm going to go to my original differential equation. So in this equation, if I replace t with 0, I can get the derivatives initial conditions. These are this. And I'm going to replace these initial conditions here. With what? With zeros. This is equal to 0 and this is equal to 0. We have not used that zeros when we are doing the calculation of the natural solution. In here we are going to make those 0 because it is the forced solution. Forced solution case initial conditions are 0. Since these are zeros, that means this disappears. And you got that B matrix multiplied initial condition of your source. So then you can calculate that derivatives here. Altogether what we've got here, IL0 equal to 0, VC0 equal to 0, dVC dt0 is 1 over C I0 for dVC dt0, dIL dt0 for this given circuit, it is equal to 0 underneath here. So that means we've finished. So that is, once you calculate by using these initial conditions, you can calculate these k values. When you replace that k values in here, you're going to get the general solution. This general solution is going to be equal to one that you found in the differential equation course. So we could now switch to our presentation. So this is what I explain to you. Maybe a bit time. First, natural solution. In Turkish it is öz çözüm. Initial conditions are zero. Initial conditions are in. Independent source removed. Find the solution. Forced solution. Independent source in. Initial conditions zero. Find the solution as you have done it, a mathematical solution before. Find the homogeneous solution, find a particular solution, add them up, and use these initial conditions, which are zero, and the related derivative initial conditions to the calculation of that case. And then you're going to add natural solution with the forced solution. This is once again the repetition. When it is natural solution, initial conditions are in. When it is forced solution, initial conditions are zero and independent source in. So you can find the general solution. This general solution is related to the inductor current and capacitor voltage. Once you find the inductor current, capacitor voltage, you can calculate all the other elements, current and voltages, by using the system equations. So that means these equations, easy to be done. So that's the end of this video then. So escape from here and stop recording.